Hello and welcome to today's webinar, Belimo and direct-to-chip cooling technologies, differential pressure control for liquid cold plates. Our presenter today is David Kandel. We appreciate you joining us. My name is Audra Shiner and I'll be your moderator. As a friendly reminder, these webinars are recorded and will be posted to Belimo's YouTube page, as well as our website. If you are experiencing any technical issues, please open the chat box on the bottom right corner and let me know so I can assist you. But without further ado, I would like to introduce to you David Kandel.
Thanks, Audra. Always appreciate your nice introductions, and welcome everybody to our webinar today on differential pressure control for liquid cold plate. Hopefully some of you have joined our previous webinars. We've had a lot of chats about different technologies that have come into the liquid cooling end of the data center business, and we're happy to show off one more today. Belimo has some specific products that allow us to do a very interesting control technique over a liquid cold plate rack. And let's just get started here. So if you joined us along the way on our presentations, you know we're always talking about heat density. How are the heat densities changing? What all these crazy chip manufacturers are doing to the rest of us that we have to respond to? So a few years ago, chip densities weren't all that hot. We could cool everything just fine by traditional air-cooled methods, but obviously some things have changed. I like to always harken back to the Uptime Institute's data where they showed us what happened during the 2010s. So here is an average heat density per rack measured in kilowatts. So in 2011, they were reporting, and this is survey data, so it's not totally holistic, but their survey respondents told them, somewhere in 2.5 kW per rack. And then by the end of the 2010s, we were at 8.4 kW per rack, which seems like tremendous growth. That's 3.5 times as much heat density over a 10-year period. That's quite a big growth. But as we're all aware, the last 5 years, things have gone absolutely bonkers in this space and created a lot of challenges that we need to be addressing inside of our data centers. So what was the big turning point? Obviously, NVIDIA is leading the way as a disruptor in this space with their computing power. The GB200 produces over 120 kW per rack, and there's some versions of this that produce over 130 kW per rack. Keep in mind that the NVL72 means there's 72 individual chips inside of that rack, each of them putting off a tremendous amount of heat, and we're generating more heat than we've ever seen before. If you've watched any one of our presentations before, you know this is what pushed us towards liquid cooling. Our source here is Vertiv on this one. This is a chart that they produced that shows off roughly the types of kW density you can cool with different technologies. So if we start way at the left in the 2010 era, where we were between 2.5 and 10 kW, well, then that perimeter crack or AHU type cooling worked, the raised floor containment. And then as we grow in heat density, we can still do air. Row-based cooling containment gets us into the 20 and 30 kW range according to Vertiv's data here. And then we shift towards we need some help from liquid cooling. So we talk about passive and active rear door heat exchangers. Those are the type where we have a liquid cooling coil right on the back of the rack, and we're running cool water through there. And the passive versions, there's no fan assist on that. We're just allowing natural convection to pull the heat out of the servers. The active ones have an array of fans on there, and obviously, as you can see here, pull out more heat. That's considered sort of a hybrid cooling because we're not bringing the liquid directly to the chip. We're just creating the heat exchange a whole heck of a lot closer to the chips than we were before. And then you get on to legitimate liquid cooling, and then we're talking about direct-to-chip cooling or immersive cooling. Let's talk specifically about direct chip cooling. It's not the only technology that's being adopted, but it is being adopted at the highest rate of any type of liquid cooling. So here we're talking about liquid cold plates. We're bringing the water directly to the heat exchanger that sits on top of the servers, and we're pulling the heat away from the chips in that capacity. So what is a cold plate? A cold plate is just what we talked about. It's a little heat exchanger. It's like a block of metal with some channels milled in it, and we're going to put our fluid through there. And they're not all that large. If you've never seen one in person, they're a little bit larger than like maybe a deck of cards, and they're designed to sit directly on top of the processor chip. So it doesn't cover the whole server, and that's why we might have as many as 4 or so cold plates on a single server, because they're sitting directly on the chips, the processing chips that are on top of there, removing the heat. We always like to point you to the Open Compute project if you want detailed information and reference designs about cold plate applications. These guys are the experts. If you're not familiar with OCP, it's a third-party think tank type organization, and they do an excellent job of creating white paper documentation and reference designs for things that are new or interesting in the industry. They have a working group that's specifically working on cold plates. They have other ones that are specifically working on how to connect cold plates to the rest of your system, how to design a cooling loop inside a technology space, how to do a CDU. They got groups for everything. Just keep in mind, Belimo's experts on what Belimo is experts on. The Open Compute project leverages the collective intelligence of almost the whole industry, so they're pretty much experts on everything. Great resource if you're looking for a lot of detailed information. Let's talk about controlling flow to the rack, because there's a few options. So we have our data center over here on the left-hand side, and this is the Belimo data center, which has like every form of cooling involved in it. But if we zoom in just over here where we're going to do direct to the chip type cooling, so you can see we can have some kind of header with our fluid coming in, and then we'll have some kind of control device that goes directly down to the rack, and we need to control that flow going into the rack. So we have a few options. The simplest option and the most basic way you can control that is to simply put a flow limiting device on there. If you know that your rack requires, say, 10 gallons per minute, I'm going to get a flow limiting device, set that for 10 gallons a minute, or purchase it based on 10 gallons a minute. And then I install that on my loop, and that's the simplest way. It's not providing any feedback or information. It's not terribly versatile in terms of its ability to change, but it does an excellent job of maintaining specific flows. So that would sort of be our low-tech solution. From flow limiting, we can go to flow control. Flow control gives us exactly what it sounds like. We don't limit to a specific flow. We can control to almost any flow. So what's pictured here is a Belimo electronic pressure independent valve, but any pressure independent valve from any manufacturer would qualify as flow control. And that would give you the ability to have an automation system or some other form of control tied directly to it to prescribe what flow you would like to have going to the rack at any given point. The value in this type of control is obviously it gives us some versatility, and on some versions we're going to get some feedback. So the EPIV from Belimo allows us to read real-time flow data. So not only can you tell it I want 10 gallons a minute going to your rack, you can verify that you're getting it. And it's also a reprogrammable device, so you can tell it, hey, we no longer want to do 10 gallons a minute. Maybe we can do 13 or 14 gallons a minute based on the new servers that we put in, or the new technology that's in place, or just the fact that next year NVIDIA is going to come out with some new animal that we don't know what that is yet, and that would probably have more heat density than we have today. So we went from flow limiting to flow control. That gives us this extra version. And then we're going to talk about differential pressure control. This is a whole different way of thinking about it. So when we do differential pressure control, and within the Belimo universe, that would utilize the Belimo energy valve and a differential pressure sensor. But the concept of controlling to a fixed differential pressure can be done in many different ways. So we don't own the rights on the ability to control to a differential pressure. We just have a solution that fits into that space. But let's talk about why you would want to control to a differential pressure. You're probably sitting there thinking, if I can control directly to 10 gallons a minute, why would I switch to some other form of control? What gain am I getting? Well, let's break down to the rack level of how these controls work. So let's go ahead and build ourselves a liquid-cooled rack. And maybe for simplicity's sake, we'll say we have 4 servers in there. Each requires 5 gallons a minute for a total flow control of 20 gallons a minute. Now, if you're sitting at your computer saying that's wildly high flows, I agree. This just makes the math simple. So don't worry about the absolute values of these flows. Just think about this conceptually. So I have a single control valve at the bottom of my loop. On the bottom of the loop, and we are controlling the flow to these 4 servers. So I have a total of 20 gallons a minute. The way that this is piped and manifold up, I'm going to more or less get 5 gallons a minute going through each of those. Now I'm fixing my flow at 20 gallons a minute. So we have the little lock showing up, excuse me, on next to my 20 gallons a minute, indicating that that is fixed. So then the question begs itself, if I have 20 gallons a minute and it's fixed, what happens if I need to remove one of the servers? So let's say I have to do service on the server or replace it with a new one for some reason or another. I pull that server out, there's still 20 gallons a minute going into that rack. What happens to that 5 gallons a minute? Well, essentially that extra 5 gallons a minute is redistributed to the other 3 sets of cold plates on the remaining servers. This is not what we would want to happen, because now we have an overflow on those 3 circuits. Even though the valve is still flowing the right amount, we're overflowing the remaining circuits. What's the jeopardy of that? Well, we want to make sure we don't overflow our cold plates in the long term. There can be some issues surrounding erosion or breakdown of the cold plate materials. They're designed at very specific flow rates, and so it's fairly important that we stay at them. Okay, let's re-examine the same thing, only now we're going to put in a differential pressure sensor, and we're going to pair that with the control valve. So we still have a design of 20 gallons a minute, but you can see we have unlocked the flow rate and we have locked the differential pressure at a 4 psi pressure drop across there. Now what happens is if I pull that server out, that 5 gallons a minute is no longer distributed amongst the other ones. Since I'm fixing the pressure, my flow will actually change to accommodate that. So I maintain 5 psi across all those servers. So I'm hoping you're like me, because when I saw these first 2 slides, I went, okay, why? How does that happen? So I took the nice looking, marketing developed slides and I put some science on them. So let's take a look at that same set of slides. But let's put a little pad of paper over here and write down what's going on. If we take flow control and think about flow coefficients and how they control liquid movement, we know that the flow coefficient is the ratio of the flow rate and the pressure drop required to push the water at that rate through whatever it is. For the sake of the discussion here, we're going to say each of these servers has a flow coefficient of 2.5 and the total pressure drop is 4 psi. And then we're going to take the flow coefficient formula and simply solve it for pressure drop. So you can see we have delta P equals the flow rate divided by the flow coefficient, that quantity squared. Why did we do that? Because if I have 4 servers in place, that means I have 20 gallons a minute. I have 2.5 CV times 4 servers. That gives me 10. 20 divided by 10 squared gives me the 4 psi, and everything works the way we want it to. The problem becomes when I remove that server, we redo the math here, We redistribute all of those things, and now the pressure drop tells me that I'm getting almost over 7 psi going across each one of these servers, where they're designed in this case for 5 psi. So we've overpressurized the servers, causing an overflow. I think this part wasn't confusing to everybody. Let's now put the differential pressure control into place and talk about how that worked, and we'll accompany it again with a little bit of math. So we take the flow coefficient formula, the same parameters of flow coefficient. This time we're going to solve for GPM because that's what we're most interested in now. So GPM equals the flow coefficient times the square root of the pressure drop. With 4 servers in place and 2.5 CV per server, the math still works. It's 2.5 times 4 times the square root of 2, and we have 20 gallons a minute. Forwards and backwards, the math still works. But here's why we get the right flows we want when we hold on to that 4 psi. With 3 servers in place, I now get 2.5 times 3 times the square root of 4, and I'm getting that 15 gallons a minute exactly how I want to. So I either just had a light bulb go off in your head or bored you to death with math you already understood. Either way, I appreciate you sitting through this with me. Differential pressure control is available in the Belimo energy valve natively, meaning if you apply a differential pressure sensor connected to the energy valve and tell it that you want to do differential pressure control, it'll ask you what your maximum flow rate is and what differential pressure you want to control to, and it will control on its own. That means it doesn't need a control signal to do this. It's maintaining that fixed differential pressure that you put in place. It is a Modbus and BACnet capable device, so you can monitor everything that's going on and have the ability to change the parameters at any time. But it gives you a lot of functionality and a lot of options in terms of how to control your product. The advanced control valve technology from Belimo are vast for your liquid cooling applications. The Belimo EPIV is our flow control valve. That's our electronic pressure independent valve. It's networkable, the flows are changeable, and it provides particularly excellent flow control capabilities. The energy valve's just kind of like its big brother. It still does all the same things, but it's a fully integrated BTU meter. It allows us to measure all of those values. It allows us to do differential pressure control and allows us IP connections as well. I always appreciate when you join us for our webinars. They always feel like they're a little bit brief and the message is to the point, but I hope you got something good out of it today. If you have questions about what we talked about today, please use the email address at the bottom of this slide, training@us.belimo.com. Any questions you put in there, that will wind up in my inbox, and I will personally respond to whatever questions you may have. And that giant QR code on the left side of the screen will take you directly to the blog post that has a little bit more detail about what we just discussed today. And it has a nice exploration of differential pressure controls and the value. So if you prefer to read about something, please head off there. If you have questions, send them back to us. Otherwise, I wish you a wonderful rest of your day. And thank you so much for joining me on this webinar.
Thank you so much, David, for presenting today. I also invite you to follow Belimo on social media to keep informed about what is happening. If you would like to watch this webinar again, it will be posted to our YouTube page as well as our website. If you have asked any questions during the webinar, we will answer all of your questions by email. And if you should have any further questions when the webinar is over, you can email training@us.belimo.com. Thank you so much. Have a great day.